Good morning. Welcome to episode number 51 of the Zoomtown experiment. Last week we were talking about random time, random destination, band destination routine to get us some randomness for our experiment. We don't want everybody running the same script over and over again. And that needed to be developed in order for us to use this next thing we're going to talk about in today's video. And that is a shortest path algorithm. Now, in the last few months, you've overheard some conversation about I got rid of it because I felt it couldn't do what I wanted it to do, and that because it was always shortest path from one location to another, all the Zoomies would congest in the downtown area or in the center as opposed to taking the bypasses. And that is very true. However, that was based on my understanding of the purpose of the algorithm. And luckily, one of our viewers, Tomek, you've probably seen him in the comments, corrected me, and I really appreciate that. Anytime I get corrected on something, trust me, I take no offense to it. I'm a human. And if somebody can present something to me that I'm misunderstanding, I absolutely appreciate it. I've spent my entire career training other people and helping them grow, so I love it when people do that with me as well. Now, let's first try to understand what these shortest path algorithms are. And I've got a website, and I'll have links for these in the description below. And I might even try to provide this particular source code on the website. It's really kind of rubbish because it's only test code. It's using some data from the actual scheduler software, but it's really just kind of patched together to get us to this point where we can run it and then explain it to you. So let's go ahead and first take a look at what this is all about. We'll go to this one here. This is out of usfca.edu, and they put together a way to animate this whole process, just for a representation. Now imagine, if you will, where each one of these circles is one of the driveways in our town. And each one of these lines represents a road. And you want to say get from road 0 to whichever road is here. We've got a total of 17 destinations. So destination 0 to destination 17. And we're going to run this. And I'm going to use starting at 0, and then what it'll do is it'll go through and find the shortest path for all the other vertices on this particular demo. And you can select different graphs and different types, large graphs, small graphs. This is a very cool way to explore what the routine is about. And you got to use your regular, you can't use your numeric keypad. I found you have to use the number keys above your alpha keyboard. So while this is running along here, and it really won't take long, it's just checking every path for every possible location. Now, in our case, these sections here that would be considered our roads, when I first learned about this particular algorithm, in fact, I was thinking that these had to be the length of the actual road segment. Made sense to me. In graphing, which is really where this came from, they don't call it a road or a length or a distance or a time. It's simply a weight. It's an assignable value between, say, vertex 0 and 7. It means nothing other than it's just a value. A smaller value would mean I can get across those 2 points very quickly. A big value would mean it's going to take a lot longer to get between it. And that's what I didn't understand. I just, from my engineering background, very rigid rules. you got a vertex at this XY coordinate and one at this XY coordinate, and that line between them has to be, well, theoretically, the hypotenuse between the two, assuming they're at different points. And that was the only thing my mind wrapped around it. And when I used this on another robotic project 5 years ago, maybe more now, I'm losing track of time here, I didn't really care about anything other than I wanted it to select the shortest path between 2 points. That's all I needed. So I used real world numbers, and it worked brilliantly for that. Well, again, we've moved beyond that now. I've become more educated thanks to Tomek, and we're moving beyond that. So this came back into the thought process over the last few months, and several of you volunteered to help me manually program all these locations. I think there was 1,024, kind of in a minimalistic sense. That would have been the bare minimum to cover every destination. It could have been a whole lot more as well. So the way this works now, though, if we just take these values at face value, say the distance of my roads, it's going to go through and calculate from any vertex to another one the roads to take that would create the shortest path. And if I wanted to manipulate it, so in our case, I don't want to go through the center of town, which would be the shortest path. I want to force traffic to the outer bypass lanes. So I could shorten up those road distances, shorten up or lessen the weight of that distance, or I could increase or make bigger the weight of the distance between vertexes within the city center. It's just a manipulation of data to get behavior that you want out of the algorithm. And that's when it became very exciting for me to really dive into this more. So we ran it, you saw it drawing all the little red lines, and these are the plots that it came up with to get from, for example, from 0 to 13, it went 2, 3, 17. So 0, 2, 3, and then 17. That would have been the shortest path to get from 0 to 17. And that's how it kind of works within our world. Now, when I got this algorithm, the only one that kind of made sense to me was one from this particular page. And this goes back quite a while when I did this on my very first robotic project that I was just mentioning. And it's very briefly described here, but the code just was very easy for me to understand. I don't know how it works. Frankly, I don't care. It's a magic box and it does what I want, which is what a great function can do for you. But this does exactly what we want. And here was kind of the magical part for me. And we'll show you that more when we get into my part of it, or my code. So these two links here, I highly recommend if you're curious about these shortest path algorithms. And by the way, there's several others as well. This is just perhaps one of the first from Dijkstra. That's the name of the fellow that created the algorithm. It's one of my first to experience and mess with it. So it became my favorite, of course. Now let's see how that correlates to what we've got here in Zoomtown. Here you're seeing some of our layout. This is actually part of the whole layout system for all of Zoomtown City here. And you'll see these are our guidelines that the robot follows, our inch markings. There's all the magnet markings, all that embedded in here too. That's all just turned off. But what is important is this. The Dijkstra algorithm, the way I'm implementing it, is going to work off a center line of road, not around the guidelines, okay? And that would be somewhat more natural like in the real world. So these yellow lines will be more of what we're going to see. So I'm going to turn off the things that won't help with the explanation. I've got dimensions here, the guidelines, some other random things, and even the center line. So I'm going to turn everything off and only turn on what is important to us for the explanation. So bear with me. I'm going to turn off guidelines, turn off road center lines. I think I'll leave driveways on, and we will turn on that. And I got some dimensions here which really won't help us for the explanation. And I think that should do it for us, so we'll work with that. Now we'll start by looking in this lower left-hand corner, get an idea what's going on here. Now, if you'll imagine on that previous example on the website, there were vertexes with identification numbers in them, 1 through such and such. Well, in our case, I think it's 1 through 76. And from my perspective, it is along the center line from this corner going to this one. That would be my first edge. This would be an edge. This is a vertex. We're identifying these, but creating the edge between them. And that way, from 1 to 2 is one length of my road. And then from 2 to 3, which is in the driveway. Okay? The edge is what we're creating to help define all of this. And that'll make a little more sense when we get into code. Now, the road itself starts here and goes all the way up to here in Zoomtown. But I needed to break it out by each intersection of some movement. And that's why we've got vertexes, more vertexes than we do roads or intersections, because we've also got destination points. But all I did was go through, start in this corner, and start labeling each one of those intersection points. I also know the distance for each edge length, actual distance, not the cheated distance to manipulate the outcome, but the actual distances. And that goes around the entire layout, all the way over to the far right corner. And there's number 76, the furthest out corner. So I went through, got all that data prepared, and then comes the fun part. That data has to be organized in such a way that we can utilize the information from this and correlate it to our streets, roads, and driveways. Now we're getting into where I started with this, and this would have literally been over a year ago. I think it was around 6 or 7 of last year, June or July of last year, when I had this code written up. I did modify it since then, but then I abandoned the concept of the Dijkstra algorithm. But this was my first go at it, and it's all functional. And, well, here's our list for our destination coordinates. Last week we modified that greatly. This one is coordinates for the vertices from the Dijkstra routine. Now this would be each one of those vertices with a number and a location, X coordinate and a Y coordinate. And I forget what the N and Y's represented here. I don't want to go back through that whole mess because we're doing it differently today than the implementation of then. But here is the routine. Here's the reference to the original source. And then the actual functions that make it all work, and the generation of the actual data, the data table that represents this. And I'm going to try to load that up. Let me see if I got it here. Okay, I did not copy it into here, but it's irrelevant at this point because we'll see it in the newer version of how my implementation is. So with that, hopefully you've got a background understanding that the purpose of this algorithm is to create a path following vertices, intersections along edges, which we would consider roads, to get from one location to the other the shortest way possible. However, by manipulating the edge length or the weight of those two vertices, we can manipulate how the algorithm functions, meaning if I lie to it and tell it that a very long road is very short, it will think that's the shortest path and force cars to go out on there, like we want for our bypass traffic lanes which encircle all of Zoomtown. So anyhow, this particular code here was a ways out, and it was very, very complex because I combined together a whole lot more processing in not just finding the shortest path, but also taking care of all the details of how to turn, when to turn, where to turn, and all these different things like that, which is now handled in a separate process that's already implemented in the scheduler. So let's get back to Dijkstra number 5, which is only test code for me to develop all the functions and refine them for our uses in the present day scheduler software. As a reminder, this code is just test code. It is not complete or functional for our final implementation. I'll still have to manipulate it because this is mixing up classes and functions. It's a hodgepodge of different methodologies. I hope to retain most of it, but I still got to weed through that. But let's just kind of go through from the actual source that I worked from that website, noted up here. We've got our class, and those are several functions that handle looking for things within that database of information, our G list, if you will. This is the function right here. This is the Dijkstra function, and this iterates through all the different possible combinations of getting from A position 0 to whichever one you want to go to, from A to B, so to speak, as we say here in the U.S. Couple little notes here. I find this one primitive but effective negative cycle detection, a kludge, if you will, but obviously it works. So then it goes through, gets all the stuff, and then there's ability to reverse that. I think this was something I added, which was able to send a robot to a destination, have it drop something off. It was an office attendant robot, drop something off or deliver a verbal message, whatever it is, and then come back. So that's the reverse path here. This function here, again, it's kind of cryptic to understand it, but the data and what's going on with all this is probably the more important part, especially at this time. But this is our graph undirected weighted list, so to speak. And here we're giving it the name G, graph, and we're adding edges. Here is edge 1 to 2 and 1 to 27. This one has a weight of 7. This one has a weight of 18. Now let's go back to the blueprint, all the way back over to this side. 1 to 2 had a length or a weight of 7 inches. 1 to 27 had a length or weight of 18 inches. So 7 and 18 respectively. This was 7, this is 18. Now what's really interesting about this, because of this, remember this is the road center line. From 1 to 2, north is up, south is down, west is left, east is right. Cardinal compass directions. So if I'm on vertex 1 and I want to get to vertex 2, and along this roadway, well, I can pretty much know that from here to here, I'm going north. From here to here, I'm going east. That is easy to define because I know the coordinate of that, I know the coordinate of this, and the coordinate of that. And that is how, somewhat in the background, the next phase of this whole thing. The routine is going to give me go to 1, to 2, to 7, to 14, etc. But from there, I've got to take that list of information and convert it to back out of the driveway, take road 1, so far, road 13, then road such and such, going east, north, south, west, all that stuff. And that's where this makes it easy to take these vertices or edges when they're combined and be able to convert that to our road system, which is actually, in this case, the northbound lane is 2 inches to the right of this, and it's shorter on south end. So it was complicated to think through, but it actually works out pretty simple. But that is this data here. 1 to 2, weighted at 7. These are all the edges. Go through all of these, and we get to 76 total edges, and that would be from one vertex to another and the distance between. So that is that data. And taking the shortest path, to get the shortest path and the total overall distance, we pass in the Dijkstra algorithm, a value of whichever our starting vertex is and our ending vertex. Now, you start thinking about that, I have to translate also the vertex numbers. Here, vertex is 3, but the destination that we would reference is destination 4. Destination 8 over here is vertex 23. So that's another translation that has to happen in this process, working from 2 different systems. So we're passing in vertex 3, 42, and it will spit out the shortest path, a list of the shortest path and the distance. Let's run this. Now from here, I'm going to copy this. I will copy this and we'll paste it into here where it's a little easier to look at. We can throw this guy away here. He'll pop up again later. Now what these are the vertex numbers from start to end of our trip. And that is the overall distance traveled at 86.375 inches. So let's see how that works on our map. We're going to start out at vertex 3, which is destination 4. We're going to go to 2. Then we're going to go to 4, which is the next one. Then we're going to go to 7, which is the next one in line. Then we're going to go to 20, which is at the center of our 4-way intersection. The next one is 33, which is this point. Then it'll take us to 34, this point. 39, which is this point. Then 41, which is this point, and then end up at 42, which is this point right here, or destination number 18. Now that is very fast, very simple, very efficient, giving us the path. And again, that could be manipulated by changing the weights for any edge. So that is what we get from Dijkstra. Now that's half the battle, because now I need to change that into roads. And how do we do that? Well, that is another function within this whole mess, but first we need to get to this section right here. This is convert, a function that I created, convert Dijkstra data to road data, meaning not center line, but actual road data, road numbers and direction, etc. And to get that, we pass it in that list that we just showed right here, that list. the starting destination, actual destination number, and the ending destination. The destination number, not the vertex. Well, this is the lookup table, and I've never used to like them, but I've really fallen into favor with them for simplicity and ease of working with and ease of remembering what I did from 3 weeks ago, kind of a thing. But this is what the whole system looks like. And this is pretty lengthy here. This is all 76 of the vertices. So this is vertex 1, vertex 2, 7 inches is the weight, and then this is the x coordinate, this is the y coordinate at the end, this is the road number and the heading. So as I'm going through this list, I only need to look here to see which destination to, and to get there was road 13, and that's a heading of north. And that is all done with, here's how I kind of help work through data that I'm getting. This is the list. 3 is the starting destination, so that's just passed into the function. 2 to 4 is the first segment or road segment. 4 to 7 is the next road segment, and so on. And then we end up at 42 is the ending destination. So I've got pairs of vertices, which would be edges in Dijkstra speak, with road and heading pairs. Search for it for the pair of vertices, so I would search for 2 and 4. The road and heading are elements 5 and 6. So going all the way back up to here, to our first one, which was 2 to 4. It's 6 inches, it's road 13, and we're heading north. And that's it. From that, I can compile all the output that we'll see printed here, which is a little bit further down past our discussion here. We go through the range of that Dijkstra list, print out what vertex, you'll hear me say vertex and vertex. In my mind, they're the same thing. Mathematically, I believe they're different things, but it works for me, and I apologize for that. But we'll print the vertex, which element we're on, and then the Dijkstra list item E. And vertex 1, vertex 2. From that, we can go through and find a match with CV1, CV2, which is in the lookup table. If they match, then that is our road, that is our heading, and that's how we get the data that we need from the shortest path algorithm. Now we'll get back to here, and what we've got is, say, 2 to 4 is road 13 heading north. So we'll go back up, back over to here, 2 to 4. 2 to 4 is road 13 heading north. Back to here, 4 to 7, which would be 4 would have been here. 7, notice how this keeps incrementing along through our list. 4 to 7 is road 13 heading north. 4 to 7, road 13 heading north. Well, how can that be? Let's see. This, let me get my road numbers back on here, which might help us. Road 13 is this one. Road 3 is this one. So we went from 2 to 4, and then from 4 to 7. And then from there, we're going to head east. 4 to 7, we're there. Our next one, 7 to 20, is road 3 heading east. Go back to here. From 7 to 20 is road 3 heading east. And we just progress through it step by step following that. So again, I didn't want to go into details on how the Dijkstra algorithm works for shortest path. It is beyond my knowledge and experience, but I know how to use it. Thanks to Tomek, I know how to manipulate it to do things I want it to do, and how we can take that data, a list of vertices, and then convert them into road directions that we need for the Zoomie to travel on. I know it's a lot to wrap your head around. It's still a work in progress. Until we get it all together, it might not make sense for most people. But hopefully you followed along, you get an idea of how the Zoomie is going to be able to get from A to B, location A to location B, through this routine and the combination of what we talked about in the last episode of random road, random time, and banned destinations. So that'll wrap it up with our discussion on the shortest path functionality of the Zoomtown experiment and its scheduler software. If you have more questions about it, be sure to post them in the comments below. We've got a number of other users here that are more advanced with the algorithm than I am, but perhaps I or one of them may be able to answer the questions for you. That'll wrap it up for this episode. Thanks again for watching, and I look forward to seeing you in a couple of weeks.